your percentage rate over.
All right, guys. So, any questions over stuff we've done so far? How you feeling about this trig stuff? Is it going okay? Some of you love it so much.
So you don't have a problem with that stuff.
So, what kind of problems are giving you the most trouble? I mean, the part of it is memorization should be okay. You just got to memorize it, got to figure out what makes sense. Yeah.
The ones that are giving me the most trouble are, I have a specific one, where it's all the ones that will be like, here's a rectangle with 1,000 angles. Over here is a number. Figure out what this is, but don't do it with any real numbers. Write sine, cosine, tangent, circle, triangle, quaternary,
Quaternary is a step that people mostly miss.
They forget. It's in there. You gotta watch out for it.
They try to use the stuff a lot, but it's just...
Yeah, that's different.
But you said there's a specific one in there like that?
45 on 6.2.
Oh, cool. Yeah. Well, okay. So this is page 449. Just to number 44. 45. And my awesome drawing prowess.
Okay. I'll do something horrible.
Funkadelic. That's X. That's 10. This is theta. So express the length X in terms of the trigonometric ratios of theta. So what you're saying, you try to propagate your information over to this side here. Well, first off, just out of curiosity, for example, what's this here?
Well, it's something of theta.
If this was 30, this would have to be. If this was 40, this would have to be 50. What do you keep doing? 90 minus whatever this is, right? So what is this then? 90 minus theta. Cool. So the great thing is in any right triangle, if you know one angle besides the right one, the other one's going to be 90 minus that thing. Now, is that going to be helpful? No, I don't know. Maybe. Just want to give you an idea of one little thing you might have to consider as you do these. Yeah.
So is that 90 degrees just for that one triangle, or for the whole?
That's in this triangle.
So the whole thing's 180.
Right, so this little piece here, I don't know. So you can maybe work it that way. What's like the most important side here, really? Because
10, because we know it.
Number on it.
all right, 10's good. It's the most useful side, but this is kind of like the side that connects both the triangles together. You got one right triangle here, you got another one there. You guys with me?
Yeah.
And that side is the common side between the two of them. So that's kind of a big one. If I can figure out what this guy is from this right triangle, I then have information to help me get into this triangle here. You with me? So some of the angles in this thing, what must this here be? Why? Because together with this one, it's got to make that right angle, right?
Yeah.
If this is 90 minus theta, this must be the thing that I add to it to make it 90.
Yeah.
Well, what do I add to 90 minus theta to make it 90?
Yeah.
Theta.
And that's also theta?
And then what's this got to be up here? Careful.
90 minus theta.
Yeah, if that's theta, that one's got to be 90 minus theta.
Yeah, so it's the same angle.
That right angle is theta as well. The top left.
Well, it has to be.
What about it?
That's theta.
That's given, yeah, that's theta. That's given to me in the problem. So that's theta. It's not 90. I mean, I drew this. That's my 90 degree angle there.
Oh, it's not. Oh, okay.
Yeah, there's the box right there. There's the 90. Cool. Okay. Knowing that everything I draw is completely not to scale. Or it's to scale of some weird parallel universe. Okay, so we've kind of worked our angles around. Now, if I can figure out what this side was, I can then set up a ratio for x using the angles. So first off, this side here, what would it be in terms of that theta? So I personally would turn this around, so I've got, let me see if I can do that now. Oh, Lord. So just take that, turn it around. Is that cool? So what is this side in terms of theta and that side? What relates this? Let's call this H. It's a good idea.
Yeah.
So we'll call that side H. Cosine, right? So if you like SOHCAHTOA, you've got the adjacent and you've got the hypotenuse, right? The adjacent and the hypotenuse, that would be the ka part of it. If you don't like SOHCAHTOA, for example, like me, you just put your angle in the base and then the x piece, that must be cosine, right? So then what can I say? Cosine theta must equal 10 over h. So h must equal 10 over cosine theta. All right, so now we know this piece is 10 over cosine theta. Yes, sir?
I think your h's are different sides.
I hope not. Let me see. Oh, yeah, it is. This is my h. Thank you. That's why I was trying to turn it, and I didn't quite make it. This is the part that I want. This is actually, the base is what I kind of want here. Yeah, that's right. Okay. So this is the h we just figured out. So how do I get this side? How, if I wanted this side? Let's call this side y. Sounds good. So that would be sine. Good. So if I say sine theta equals y over h, then h equals y over sine theta. Well, actually, y equals h sine theta. You with me? And what's h?
H is that.
It's 10 over cosine theta. Crazy. So there's a lot of one of the most important things here is to realize that that side is the one that's shared between the two right triangles. So that's a big one to kind of get a hold of. I can get that side from this triangle and then help me apply it into this triangle. So now I know that this side here, y, is h sine theta, where h is this. So I get 10 sine theta over cosine theta. Of course, there's a way to get there a little bit quicker. Well, we got there eventually, 10 tangent theta. So if this side is 10 tangent theta, and I want to know what that side is, I just now just got to figure out what trig function would relate those two sides.
That's a sine of that.
And I don't have to use 90 minus theta if I don't want to. There's theta there, right? So now to relate these two here in relation to this theta here, what trig function of this theta would relate these two sides? Good, sine. So sine of theta equals the y side of the hypotenuse. You with me? Now, of course, the labels we're using doesn't have to match that, but that's the idea. This is the y side over the hypotenuse. So x equals y sine theta. We know what y is. Funky-delic. Is that the only way to get there? Hell no. I went a little further than I had to because I turned my triangle around incorrectly. So thanks for catching that. There's a little bit quicker way to get there. Is that an easy problem? No. But this is a good example. This is not the best example. This is a good example of just feeling free to play with stuff. Playing with, you know that trig functions are ratios of sides. So you say, okay, I know that side, and I want to know that side. So what can I set up to relate those things? So from the very beginning, I could have used, let's see if I turn that around. Yeah, I could have used tangent to relate these things, but we got there eventually. Tangent. But this was y, this was x. I could have used tangent from the beginning. And that would have worked fine. So here I get x equals y sine theta. Y is this. I just got to throw that in and I'm done. That should feel familiar. You see that kind of problem on SAT all the time. Not exactly this, but playing with angles and trying to get them to work out. Now it's kind of the same idea, but we're playing with ratios of sides of triangles. What do I know? What do I want to know? What do I know? What do I want to know? And what trig function relates those two sides? I can shut a root down pretty quickly. Yeah.
You never find out what theta is?
You can't. We don't have enough information.
So your answer was
If I just knew one more side, I could figure out what the angle is.
your answer was 10 times theta sine theta?
Exactly. That is
Semi?
not satisfying, but based on the fact that we only have one number in this whole thing, that's not bad. Yeah.
Well, that's no problem because it's good.
Yeah, exactly. Get it in terms of theta. If they would have just given me one more side, I don't care which side, if they just really give me one more damn side, I could have figured out what theta was. Yeah. Yeah.
So that one is, can you use tangent of 90 degrees to find the y over x?
Not really.
For the hypotenuse?
Because you can never really use, if you try to apply the trig functions directly to the 90-degree angle, it kind of falls apart then, because the opposite and the adjacent all goes to hell, because then they're all the same as hypotenuse. Opposite from it would be the hypotenuse. And that's really why sine of 90 is 1. If you think about it, yeah. Does it lead to anything useful? Not really. Yeah.
Can you solve the 6.2 number 9? The sketch of triangle? Page.
Oh, yeah.
Thank you.
Alright, so if I had this information, I really truly don't, if this came from a specific triangle, I can never hope to, with 100% certainty, get the triangle it came from. But I can sketch a representative triangle. Why can I never get what triangle this truly came from?
Because it doesn't give you units of sides at all.
Yeah, I don't know what multiplier it might have been used. I know it would reduce to 3/5, but I'm not sure exactly what multiplier they were using. But I can draw the representative triangle. Where would 3 have to be and where would 5 have to be?
3 on 5 on the board.
3 is the y piece,
Y piece.
and 5 is the hypotenuse. And then they ask you to find the other 5 trig ratios. So I can immediately find which one, without even that. What do I know just based on this? Cosecant. What would cosecant be? 5. I can't get any of the other ones until Pythagorean theorem, right? Like, I don't know. Until I get that last side, because all the other ratios depend on that last side. So the two that depend on the east sides are sine and cosecant. Everything else involves this side somehow. So how do I get that side? Yeah, 25 minus 9. 16 square root of 16 is 4. And there's your 3, 4, 5 triangle. One of the very few, relative to the infinite number that have nice whole number sides.
Oh, one more time. The one you said, like the sine squared plus cosine squared.
Yeah.
And is equals to what? Is that the identity?
Yeah, you could use that. You could use that here to figure out what cosine is. Sure. Especially because you know it's got to be positive because it's supposed to be a real triangle with nice positive sides. Is that cool? A problem like this, I enjoy putting on tests and quizzes. Yeah.
You do 15 on 5.
15 on 5. 2.
It's sort of different stuff. This was a good one. But there was a lot of these. Getting one from this out, you gotta do this times that, and this times that. But it is. You get pretty much these just they took it. Well, these ones. Actually, these ones took me. So I wasn't considering that. The last two chapters. I had it in this weekend.
So, yes, ma'am. This is still section 5. Oh, sorry. This is section 5.2. So what do you guys think is going to be part of my instructions on this if I give this to you in a quiz or a test?
Tell us how many radians.
Reference angle.
There it is. Sweet. So find the reference angle, show me your work. Sorry. Where is it? It's a decent song at least.
Sit down.
Somebody has kidnapped Adele in their backpack. Where would that be? What quadrant would that be in? 11 pi over 3? And why would it be the third? What is 11 pi over 3? Almost.
It's almost 4.
It's almost 4 pi. Because 12 pi over 3 would be 4 pi. And where would 4 pi be?
Right here.
Here.
Second part?
This would be 2 pi, 4 pi would just be going around twice. So it's almost 4 pi. It's off by how much?
1 pi.
1 pi over 3.
1 pi over 3.
It's pi thirds away from being 12 pi thirds. Guys. So it's right. So how far away is it again?
Pi over 3.
Pi over 3. So you notice part C is referencing the same angle.
Goes backwards.
That's a good use of the word referencing, Jeff. So now I can relate that. Secant would be positive or negative. Because secant is related to what? Which one of the three? Cosine. Cosine is x, and x here is positive. So no, secant's going to be positive. So this equals secant of pi over 3. So the value will always be the same as the trig function of the reference angle. It's all a question now of is it positive or negative. That's the beauty of these. You only have to memorize the first quadrant values. Now you got to realize secant is really 1 over cosine. So now you can say, okay, this is 1 over cosine pi over 3. And if you want to take it even one step further to make it more close to what we originally started with, pi over 3 is what degrees? 60. But I really want to get you guys to not even do that step. Get more used to that staring you in the face. What is cosine of pi over 3?
1 half.
1 half. Good, because that 60 is farther away from the x-axis, so it should be smaller. So 1 over 1 half. 2. I get way too many people that stop right there. It makes me concerned. You know how to do that. If you know how to do that, do you realize you should not stop there? So yeah, you got to keep going. That's 2. What about cosecant?
So cosecant.
It's all the same work I just did, except
sine.
cosecant now is based off of sine, and so it's going to be negative.
3 over 2. 1 over.
So see, I just kind of skipped a few. So it's equal to the negative cosecant, which is 1 over sine.
Would be a negative.
And the sine of pi over 3, of course, has to be root 3 over 2, the other guy.
2 over square root of 3.
Yeah, 2 over root 3.
2 square root of 3 over 3.
I love it, which you must rationalize.
Negative. Yay!
Right, the last step on those is just to rationalize it. Sort of like the last step is to reduce your fraction. Same idea.
So this is a negative, but then it
Yes, sir.
becomes positive, and then that's secant.
Because cosecant is based on sine, and then the fourth quadrant sine is negative. Y is negative. Yeah. Do you guys see how I wasn't insane, especially if you like SOHCAHTOA?
Are you sure?
Well, at least not for this reason. If you remember, sine is like y, cosine is like x. It just makes so much more sense in other situations. And then finally, secant and negative pi over 3. This is kind of a silly question because negative pi over 3 is the exact same angle. We already did secant of that angle. So it's just going to be 2.
2.
Not negative because, again, it's based on cosine. Is that cool? All right. I like that.
The negative just means it's going in the opposite direction.
The negative on the angle?
On that.
Yeah, on the angle it means you don't go this way or you just go that way. And that's why these are all referencing the same exact location.
So positive is counterclockwise.
Yeah, positive would be counterclockwise.
Section 6.1, number 74.
Is everybody cool with that one? Okay. 6.1 number. Oh yeah.
It also helps us out getting a circle on our first mistake.
Oh yeah.
Remember this.
Because I had to cold turkey, circle style. So because I remember the first two audios.
Before you start problems, draw it, remember it, and then you can use sorting for your own good. Please draw it.
So to do other things too.
You only have to draw the first one.
And the pile was 50 out, we can cut everything into 6.
Okay.
Like they do on the boat. And just figure out that's a 5. It's just 2/3.
I've drawn this very small. I'm not sure. So.
Yeah, of course, these are
500 miles.
This is like some astronomy stuff right here.
This is still section. No. Now this is where we.
600-700-year-old astronomy.
Please tell me it's the right problem. Who asked me that question?
Looks like pizza.
It's right. Good. Because if somebody asks me a question, I draw all this stuff, and they say, "Not that one." All right. So here's what and they give you the picture of what's going on. So if you're here at a certain time of day, the sun is shining directly down this well. So you can see the sun, the whole shape of it down. So it's going right down the well. And 500 miles away from there, at the same time of day, it's hitting at a 7.2 degree angle with directly down. Does that make sense? Sort of. That angle is in a bad place. Where would I rather have
The very bottom.
information like that?
Your angle.
I'd rather have it like inside the circle somewhere.
Yeah.
Now, what's true about these two?
They're the same angle.
They're parallel.
They're parallel.
That's like
11. And so this would be a, who remembers that term? Transversal of those.
Yes.
Right? So this and this, they are
Same.
corresponding. Good. So they must be the same. So this has got to be 7.2 degrees. Obviously drawn to scale. Maybe slightly exaggerated. How are we doing so far? Is that cool? Okay. So what they're really asking now, what are they asking?
I don't know. How big is the
Find the
Earth?
radius and circumference of the Earth. So I want to find this distance here. Actually, I want to find just this distance here.
7.2.
So what does this really represent?
The arc.
Be more specific. Arc length. And what's the definition? What's the formula for arc length?
Or theta.
R theta. So this problem actually becomes a lot easier than it looks when you first look at it. So you're right. When you first look at this, you're like, oh, this is some kind of astronomy, physics, mutant child, monster problem. When actually it's not that big of a deal at all. They told you the arc length, I know the degree that it goes through. So I just got to plug those in. Now the one thing to be careful about, the most common mistake that people make before I start throwing numbers in, theta must be in radians. That's the most common mistake on this problem. Degrees are made up numbers. I can't throw them directly into an equation. If I have a trig function buffering things, trig doesn't care. Trig takes the degrees and it says, oh, you mean this situation? Cool. There's no trig function here. Shit. So I need real numbers. So how do I convert that into
7.2 degrees?
radians?
Pi over 180 degrees.
Good. 180 degrees cancels. Pi radians. So whatever the hell that is. So you get, what's the arc length? What's S? 500. Equals R times theta, which is this mess here. And I just got to solve for R. Is that cool? And of course, once you got R, the circumference is easy enough to find. And you can get the circumference, actually. You could have gotten that first.
Yeah, that's what it
How do you check yourself? Go to Google and type in radius of Earth. And there you go, you can check yourself. Obviously his observations were not computer based, so you might be off a little bit. I would give him some leeway.
It's very, 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 very.
Trying to figure out the radius of the Earth from looking down a well. I'd say, okay, I'll give you a little leeway. Maybe some medication. Is that cool enough? Is that all right? Solve for R and then the rest of it's easy. Anybody know how to do this? How to get the circumference directly without doing part A first?
Yeah, 2 pi r.
Take the formula area equals to half r square, something.
I don't know R. In fact, I don't need R. If I know this much is 500 miles for 7.2 degrees, yeah, 360 divided by that times 500. I can just do that ratio.
Pi square. So angle
This is
square.
7.2 out of 360 degrees is 500, so I can work backwards to figure out what the whole thing is. Do you have to do that? No. You can figure out the radius first and go like that. What do you guys get for the radius? Did anybody try it yet?
3978, 187.
3978? 0.87? What'd you get?
There's an issue with
That's right. 3978, 27.
close.
Okay, alright. And now you can figure out part B. Now how close was his approximation when you can look up the radius of the Earth?
It's very close.
Actually, you can look at number 75.
Pretty close.
The radius of the Earth is 3960 miles. You got pretty damn close.
It's only 98 miles off on the circumference.
Not too bad.
So that
Well, the Earth's a little tricky.
Okay. Anything else from the homework?
You couldn't even put it on the internet, right? You could publish it in nowhere.
Yeah.
78.
Put it on the
Oh, yeah.
Oh, yes, please do 78.
Shoot this man.
This sounds like an old pub or something. The Tethered Cow. Not sure what their signature drink would be. The Tethered Cow. place at. That's you drawn by me.
No, he's not. Super nice.
So the whole thing about this is find the area that the cow can graze, and they've sort of shaded it in for you. And this is cool, kind of spirally shape to it. The cow can obviously. I got roughly with the tongue. So you can go here. So you can figure out how much past this he can go. But then, of course, the minute he does that, he's got to come in because of the fact that the rope is going to start to, it's going to stay here and go like that. So then what's the radius of this little circle down here going to be? Well,
40.
and how do you know that? Because that's 60. Once the cow is there, that's 100. So how much past that does the rope go? 40 feet. That's kind of like the new radius for the circle when you're down here. Do a similar thing up here. So when the cow gets up here, how much past there is he? And that'll be the radius for that new circle that you can go past here. It goes around. That's kind of nifty. Of course, this will come up like about somewhere there, something 10 feet below, because once it's 40, it's 40 there. Yes, sir.
Wouldn't you get stuck on that further corner towards the inside? On the top?
Oh, yeah, so once he's, let's see now, once he's here, he's got, what was this? This is 50, so this will be 50. And then once he's here, how much does he have here to play with?
20.
So my picture's nowhere near as good as the picture.
30.
So here he's got, it's 100 feet here.
So 50.
There's 50, so there's 50 here to play with. Right? It's not to scale. Then he can shoot out to here until he gets to here. This will be 30 feet. Good, because it's got to be 50, it's 20 and 30. And so that's the new radius for that part of the circle there. So you've got sectors of circles that you have to find the areas for, but you know what the radiuses are for each of those circles. So you've got one big ass circle here in the middle that covers basically from here to there. So that's how much that circle is going to be. A quarter. So you figure out the circumference of, the area of a 100-foot radius circle, and you take a fourth of that. And you do similar things for this down here. And then this guy is going to be interesting. It's got a quarter when it's a 20 feet radius. Sorry, 50 feet radius, and then a quarter when it's at 30 feet radius. So the whole point of this problem was to figure out what the radiuses are for each of those circles that it can sweep out. And they do a decent job of showing you the picture. You can see where he's been grazing because there's less grass there to make it nice and paler. But they kind of show you the shape it's taking, and you can kind of see it happening. When he gets here, the rope is going to get stuck here, and then his radius has effectively been shut down a little bit. All right, so I can sweep it out, and then something like this, and oh, I got less radius. All right. And much better than PowerPoint. Yeah, I'm not sure what that means. That's not a bad picture for me, actually. My aunt. Is that enough to get going on that? Is that find the area of this circle, take 1/4 of it, find an area of this circle with 40-foot radius. 1/4 of it, find the area of a circle with 50-foot radius. And an area of a circle with 30-foot radius. 1/4 of it. Add them all up. Okay. I don't know if this farmer's going to make his life so complicated, but
I know you could have 3/4 of a circle with the cow on the other side of the barn.
pretty much. But there's a cliff right here. Yeah. Five two. Oh. 5'2". It's interesting. It's about a bungee jumper. So very often you see, if you ever watch video of bungee jumping, you see them go down. You don't see too many of their oscillations, but I've actually never bungee jumped. Anybody ever bungee jump? It's got to be really annoying. You're like, oh, that's so awesome. And they're like, when are they going to take me off this damn thing? All right. Get away from a bird. But this talks about sort of like that. At time t seconds after her jump, her height in meters above the river is given by, and it's controlled by. This is kind of a neat equation because it's sort of close to what it would be in real life. It makes sense there's a cosine piece because you're going to get the whole wow, right there. Doesn't have to make that sound. What's this piece here? Kind of, but
Natural law.
you see this kind of thing also when you describe plucking a guitar string. Right, over time, the sound, of course, dissipates. The string eventually stops moving. It doesn't vibrate forever, or else we'd all go insane. Every guitar string ever plucked will just go forever. So this is what's called the damping of it. It gets damped over time so that eventually it goes to nothing. It's a really cool graph. When you graph it, you can see this oscillation getting smaller and smaller and smaller. It's really neat. The e to negative kind of just it's a ceiling that's coming down on it. It says you can't go. Oh, crap. So this is the amplitude of this. How about that? Is that even better? And the amplitude gets even smaller, because what happens when t gets bigger, e to the negative, it's going to go to 0. Okay, enough of that. The whole point of this problem is, are you able to plug this thing into your calculator correctly? Because they give you the values of t, you just got to figure out the values of ht. So they tell you 0, 1, blah, blah, blah. So it's all about plugging it in the calculator correctly. Making sure that you tell the calculator what's the exponent on the e, so forth. Is that cool? Okay. To me, I'd rather graph that bad boy. If I'm you, I would graph that thing. This thing.
Another one, I don't know which one it is. I have it down.
Okay, sure. Here. Okay, got it. So page 440. This is section 6.1. Like number, I think it's basically that. Yeah. Number 61, I think. Yeah. Oh, it's even better. 62 is more directly. 62A, for example, has this kind of thing. If the area of this sector is 12, and the radius is 0.7 radians, I mean the angle, find the radius. So what's the formula for area of a sector?
S.
Careful, that's the arc length.
Half r squared theta.
I love it.
Half by r squared over 2.
1/2 r.
And it's really 1/2 the base times the height. The height is r and the base is r theta. R times r theta is r squared theta. So you've got the radius, you've got the area, you can solve for the not the radius. You got the angle, you got the area, you solve for the radius. Is it cool? No. We know the area is 12. On your problem, I think it was 14. Same idea there. Area is 12. I don't know what R is, but I know the angle is 0.7 radius. Solve for R.
You don't want to change this to radian? This degree, the angle?
It already is radians,
Oh,
0.7 radians, yeah. Cool.
Good.
But you're right. You always got to make sure it's that way or you make it that way, yeah.
Oh.
So then you got 24 divided by 0.7, square root. That'll be your R. Take a positive root. R. Is that cool? Okay. It's roughly 5 point something.
5.6.
Yeah. Okay. I mean, that's the kind of problem you see all the time. It's almost like having a word jumble problem. I always hate that when teachers have said, unscramble this word. That's one of your terminology. What the hell does this got to do with it? This thing is almost the same. It's the equivalent in mathematics. This is, do you know this formula? Can you plug stuff into that formula? That's really all that problem is. It's algebra problem. Solve for the unknown thing. Plug the other stuff in. Yeah. Okay. All right, so what we're doing today, we got through, I think I need to finish up 6-4. Possibly. Yes. And then I want to attempt to finish out 6. See what happens.
And there's all those little pieces in the middle. The other one's going.
But let me just give you a problem and see what you think about it. What can you write down related to theta? What can you set up from this triangle?
So you can do sine, cosine.
Yeah, tangent theta equals 7/3 y over x. Cool. Now I'm asking you to go one more step. I want to know what theta itself is. Well, what's going to help us do that? This is basically a formula. This is not a formula, but an equation. If I had cube root of theta equals 7/3, I would cube both sides. Because cubing is the inverse of cube rooting. So here, what do I want to apply to both sides? Inverse tangent. Also known as the arc tangent. Just to let you guys know, inverse tangent is also called arc tangent. I very rarely call it arc tangent, but the book will show that every now and again. I just never really got into the arc tangent thing. So tangent theta, 7/3, I have to do inverse tangent to both sides. So the tangent and the inverse tangent cancel. Now I just got to do that on my calculator. Who remembers for the tangent, where did we go from to make it invertible? Remember the whole problem was sine, we had to cut down the domain. Cosine, we had to cut down the domain. Tangent, we just have to look at one piece of it so that it passes the horizontal line test. So what did tangent go between?
-5/2.
Yeah, -5/2. A 5/2. So the thing you have to be a little bit careful about is the fact that your answers could come out anywhere between these. So we had to do this to tangent just to make it invertible, because if I kept going with all the tangents, then it wouldn't pass the horizontal line test. So if the domain of my tangent had to be cut to this, that means the range of my inverse tangent will be this to this. If you get a negative angle, and I'm talking about a triangle, that's freaking me out a little bit. Can't have a negative angle inside a triangle, so you just got to realize it's a reference angle. You got to actually come up with that, what that angle is. So what do you get here? I like it. So I'm seeing who's got their stuff in radians. So in degrees, I get 66.8 degrees. In radians, I get 1.166 roughly.
Is there a rule, like if we're doing radians and then at point format, you should go to 2 decimals, you should go to 3, or is it just like...
Kind of depends on the situation. What I always say is, if you're going to do more with this, don't round at all. Get to know your memory buttons, right? You never round to the end. Then I'll let scientists do their thing with their sig figs or whatever, right? But in mathematics, what's the most important is you don't round to the end. It's the same with science. You don't round to the very end, and then you figure out how many sig digs you want. But here, I'm not going to do any more with this. So a couple, 2 or 3 is fine. Yeah. Let's say 1 radian, that's kind of a problem. Okay. How big is 1 radian?
Just a little under 66.8 degrees.
Careful. If I have 1 radian, how do I convert it to degrees, for example? Because degrees, we just have a better feel for it.
180 over.
Yeah. Pi radians has got to go down here so the rad goes away. So it's 180 divided by pi, so it's like 50 something degrees. Does it make sense? You guys kind of with me? Okay. This 45-degree angle, pi over 4, is a little less than 1. Pi is 3.14. Right, divided by 4 is a little less than 1, so it's going to be a little bit greater than 45 degrees, so that kind of makes sense, 50-something degrees. Cool. Okay. So this kind of thing is going to show up now. We're going to the point where we want to fully solve a triangle. So find all the angles, find all the sides. Right, so sometimes we're going to have to do these inverse trig functions to figure out an angle, and so forth. Right now we're doing very more basic problems like, I mean, you're going to see the ones exactly like this on page 467, 15 through 20. Here's a more interesting problem. This is a little bit more interesting.
Okay. All right.
So we know one answer right off the bat. We should.
0, right?
That's a theta.
No, so theta is less than theta?
No, sorry. That's a 0. That's a theta. So what's the basic answer to this? What's the reference angle answer to this?
Sine equal 1/2.
Yeah, it should be where sine is smaller. So where's the y smaller?
X will be bigger.
The x should be bigger. So it should be closer to 0 degrees. So it should be 30 degrees, pi over 6.
And then over here on the other side.
Where else is e equal to 1/2?
On the other side.
On the other side, yes. Not only the first quadrant, but also the second quadrant, because sine is positive in both.
Yeah.
So now all you got to do is, that's a reference angle now.
Yeah.
So if you make that a reference angle,
Here.
go back 30, where do you end up?
At the 100.
150 degrees. Or pi minus pi over 6. 5 pi over 6.
5 pi over 6.
Oh, cool. Is that cool?
Yeah, I actually get that.
Now let's try a little bit harder problem just like that. Yeah.
harder.
Like this on the test, we have to give you both degrees and radians.
No, I should say,
You will specify radians.
yeah, I have to. If I don't specify, you can give either one. Yeah. If I say give both, then that's what. So what about this here? Same kind of idea. Uh,
So first we have to convert that into something besides radians. 1.7.
Now the difference, of course, the main difference between these last two problems is that one I could do without a calculator. You should be able to do it. This one, can't possibly expect you to do that without a calculator.
1.7.
Unless you have ultra photographic memory and you remember the entire range of trig values. I don't think so.
Is that in the third quadrant?
Say
In
it.
the third quadrant?
It's got to be, well, where's tangent positive?
3.
The third quadrant and
1.
the first quadrant, yeah. So I need two answers to this because I'm asking for all the way from 0 to 2 pi. So you need a first quadrant answer and I need a third quadrant answer. All right?
Yeah.
So when you just do the inverse tangent, what do you get?
1.04.
And here, kind of, what am I asking for really here? Radians. So over there was degrees, because I started with degrees. Here I'm kind of asking, it's got to be radians.
It's a 90 degree 2 pi.
So again,
2 pi would be 270 degree or
360.
360.
Yeah, twice 180.
So 306.
So make sure your calculator's in radian mode. What answer do you get when you do inverse tangent of 1.7?
1.1.3.
Do it again. 1.04?
I got 306.
Okay. And like we just figured out, one radian is 50 some odd degrees. So good, that's the first quadrant. Now how in the hell do you get the third quadrant answer? So we have 1.04 radians is one answer. Now again, this is a reference angle, so how do you get into the third quadrant?
180 minus that, or 2 pi minus that, or pi minus that, whichever you want to do.
Yeah, you actually do pi plus that. Because you want to go a full, not full, but a half a rotation around from there. You with me? Or the other way to look at it is you want to go to pi and go 1.04 past pi. So the other possibility would be 1.04 plus pi. Which you might as well approximate that because we approximated the 1.04. You guys semi with me there? The thing to realize is when you do an inverse trig function, you're getting a reference angle. You have to make sure that either one, you answer all the questions, or two, you get the angle where you're supposed to be. If they said the angle was in the third quadrant, I better not say 1.04. That's wrong. That's the first quadrant. You better give me this answer. So we want to approximate that. You do it, Jeff? Okay. So that one or that one. Those are both answers in that range. You guys understand why it had to be the first and third quadrant? I mean, that I went in knowing, because tangent is only positive. Tangent is positive in the first and third quadrants. That's all. Nothing amazing there. That's why this one was the way it was. Sine is positive in the first and second quadrant. That's why that range gave you two answers. If you use that range of the cosine question, it's kind of silly because then I'm just going to get the one answer. It's only positive then in the first quadrant. Okay, hopefully. Let me see, what else can I throw at you? Oh, perfect. You'll like this. Now, I hated it when I saw something and I had no clue until the professor said something. I'm like, well, shit. Of course. That happens so much. And you've got to let it, it's just going to happen because you're seeing a lot of this for the first time. I don't know if any of you guys have any idea how to even approach this kind of problem. Besides throwing. It in the calculator. That was kind of freaky.
Yeah.
Alright. I have a webcam in here somewhere.
You got a camera in the class.
Yeah, well, it's not streaming though. Alright, anyway. Do you have an idea? No, it would be awesome if that was sine of inverse sine. They would cancel, right?
You use the tangent.
Let's look at this really a little more closely. If I have inverse sine of something, of x, what does that equal in general? What physical thing? What is it geometrically that it gives me? It gives me an angle. I love it. You guys with me? How do I know that? Because the input of a sine is an angle, so the output of the inverse sine is an angle. Little punctuation mark. So that means I could look at it like this, right?
So can we just make the top one equal theta then?
Not quite. Doesn't really get me anywhere. I'm replacing something with more information with something with less information. Not a good idea. But remember when we had this kind of thing, we could create a reference triangle for this. So I want to make a triangle whose sine of an angle on the base is 7 over 25. Don't you remember? This is basically saying the same thing as that. Are you guys with me? Inverse sine of 7/25 equals some angle, therefore the sine of some angle is 7 over 25. Can't I draw the triangle that represents? And then can't I find the cosine of the damn triangle that that represents? So the real thing to realize is this is an angle. So all I'm asking for is the cosine of this angle. Well, what angle is this? Well, it's the angle whose sine is 7 over 25. Oh shit, let me draw the triangle and see what's going on. So what would this triangle look like? Like that, Jeff. Yay. And where would what be?
25.
25 is the, I love it, and 7 is the y part. I love it. Cool. So now to find the cosine of that angle, I just have to find the x part. Put it together. So that problem now becomes very simple. When you first see it, you're like, how the hell am I going to do that shit? Do I have to change cosine into sine somehow? And you actually sort of could. Screw all that. Let me just go directly. What's this side going to be? That's right, 24. Check me on that. It's one of those Pythagorean triples. So the cosine of this angle must be 24 25ths. This is this angle here. So in that case, I can call it theta just to give me some room to put it, right? So this is that angle. So what's the cosine of this angle? I just have to make the right ratio. A lot of what we do kind of reminds you that trig functions are just ratios of sides. As we do more and more with them, it's hard to realize that that's all they are, right? How could it just be that, Jeff, when it's this complicated? Well, it is. It's just that.
How do we got the base 24, sir?
Say again?
The base 24.
Oh, we did Pythagorean theorem.
Or the base x squared plus y squared.
25 squared minus 7 squared, and then square root it.
And is it, what is it equals to?
Do it again.
Is it the x squared plus y squared equals to, what is the, what?
H squared, if you want to do it that way, yeah. Okay. One last example, and then we'll get into some new stuff, and then we'll take a break.
Draw a triangle.
So again, you gotta be careful now. This is not reciprocal. Yeah. There's no real difference between those two problems. You got to get past caring if you have numbers or variables. You got to get past them. Numbers and variables, they're both just symbols for stuff. Who cares? So I can do the exact same first step, which is what?
Draw a triangle.
You got to draw a triangle. So what sides am I talking about now for this guy? This is x minus 1 over 1. That over 1 is useful. Don't forget, there's always a ratio in there. So the thing by itself, it's over 1. What sides is that? What's this side? Careful. So it's a cotangent now. Cotangent is x over y. So this will be x minus 1. And this will be 1. Is that cool so far? Okay. And to figure out the secant, what side do I still need?
Well, x.
We got the x side.
We have to figure out h.
To make secant, I need h. Yeah. So what's the hypotenuse going to be?
It's going
Square root of 1 squared plus x minus 1 squared.
How unfun is this?
It's awesome fun. You guys with me? Yes, ma'am. So again, math does not care what symbols we want to use.
Care.
Numbers are just symbols. They have certain rules on them that variables don't follow because we don't know what number they are. But they're still just a symbol. So what's the idea of Pythagorean theorem? 1 squared plus x minus 1 squared, take the square root. Right? Pythagorean theorem doesn't give a shit what you put on the sides. It just says square them, add them, square root it. So this will be the square root of 1 squared plus this thing squared. And you don't care, because now you just make the ratio that you need. Secant is related to cosine. So cosine would be x piece over hypotenuse, so secant must be hypotenuse over x piece. So this would be root x squared minus 2x plus 2 over x minus 1. Don't try to do anything with that.
So secant. So we know that.
Is that cool?
Root of x squared minus 2. Secant of that angle.
Some of you guys are still digesting, I understand.
Oh. It's h over x.
Only they made math fantastic. Okay, so let me get, I have an idea where we're going and we'll take a break.
Oh boy, law. The long arm of the law.
So I kind of remember when you first hit this, when I was going to school, and I was like, oh, thank God, because I sort of, now obviously I was a major geek, but I always had a problem with the fact that there was so much, oh, now I'm even beyond that. I'm a freaking corporal or whatever the next level after.
What is geek?
Yeah. So what was it, Obama said?
Major General.
From a mind meld and the Jedi man, yes. The thing I always hated was the fact that you can do so much if you know it's a right triangle, but you can basically not do shit if it's not a right triangle. And I'm like, sometimes you can draw the height in and make right triangles and do something, but there's situations where you just can't do a damn thing. And I hated them. Like, why does it have to be a freaking right triangle? There should be rules, there should be something. And sure enough, the really cool thing, I love law of cosines, and I know you won't hear many people say that, but because it just kind of shows you the Pythagorean theorem is a specific instance of a more general rule. The Pythagorean theorem is missing a part of it that is 0 when you have a 90-degree angle. You guys kind of with me? That's a really cool idea. So it doesn't change anything of what we've done. It just opens the door to more generalized stuff. So I love law of coincidence. Law of signs, and students don't really like law of coincidence too much because the work is a little bit worse. The law of signs looks a lot better, but it opens the door to situations that have 0 answers, 1 answer, or 2 answers. And it kind of brings back a specter of something from geometry. Some of you guys might think I'm going in this direction. Remember this stuff?
No.
And then the infamous SSA, which is also more generally known as ASP. And the nice thing is that's the pace that brings us to the part where you have ambiguity. I like that. Ambiguous situations thing. So it's really nice that you can write it as the word ass. It makes it very simple to remember, oh yeah, that's the ass. That's the one that's going to give you trouble. And what are these references, by the way? Hopefully everybody knows.
Sides.
So here I would know all 3 sides and no angles.
Negatives.
Here I would know, this is very specific. I know the side, the angle, and the other side. Whereas this one I would know a side, and then an angle. Maybe coming off of there.
The ass is. That's the ass.
That's the ass one,
That's the
yeah.
problem. That's the problem.
So, and there's some more. So that's where we're headed. We're trying to make these more generalized rules that work for triangles that aren't right triangles, that are more,
Ain't right.
could be anything. So let's take a break, and then we'll get into that. So come back at 2 o'clock.